Hello, I'm Tommy Lau. Now I would like to demonstrate my MC18 project, which I will do channel length scaling for the FinFET module and simulate the FinFET module inside the MUGFET tools that provided by the NanoHUB website. Without further ado, let us refer to the tools. And this is the MUGFET tools from the NanoHUB. And we can set the parameter of the FinFET in the tools. In this tool, we can set the device type, the structure, the material, the environment, and also the simulator for the FinFET that we need to simulate later. So in this project, we only need to change the structure, which is the gate length of the FinFET, to change to 60 at 3 different values, which are 60 nanometer, 45 nanometer, and also 30 nanometer. Then other parameter we keep then as default value. By the way, we need to also to enable the Gaussian doping flag to enable the Gaussian doping. Then for material, environment, and simulator, we let them as default settings. Then we can do the simulate. And after the simulation, we can get various curves that explain the characteristic of the FinFET. In this project, we only need to look at the IV characteristic, which is the ID and VG, drain current, and also the gate voltage characteristic of the FinFET. And this, the IV characteristic of the FinFET, will be print out at the curve here. From the IV characteristic curve, we can obtain the information about the threshold voltage, threshold swing, the I-on and I-off ratio, and also the drain induced barrier lowering value of the FinFET. Then after the simulation, we can change the gate length to other values and do another simulation. Then the difference between the different gate length will be checked through the parameter that we obtain from the IV characteristic curve. From the tabulated result, we can obtain the trend of the threshold voltage, the sub-threshold swing, I-on, I-off ratio, and also the drain-induced barrier lowering value when we reduce the gate length from 60 nanometer to 30 nanometer. As we can see the result, when we reduce the gate length, the threshold voltage also reduced. This means that the gate will have a weaker electrostatic control over the channel. And also, this means that the device also will turn on at a lower value of the gate voltage. This might increase the switching speed of the FinFET, but it also might increase the leakage current of the device. Next, for the threshold slope, the slope is increasing when we reduce the gate length. This means that, and for the I-on, I-off ratio, it shows decrement. This means that the difference between voltage, high voltage and low voltage becomes smaller, and it will impact the noise margin, and also reliability of the reducing gate length will reduce the device ability to effectively switch off, and leads to a higher steady power consumption FinFET. And lastly, for the drain-induced barrier lowering, it shows increment. This means that the drain electric field will become more easily to penetrate, to pass through the channel region when we reducing the gate length. This might because the potential barrier at the source will become smaller, even at a very low gate voltage. And that's all for my project. Thank you for watching.